In the last lecture, we were discussing the Karush-Kuhn-Tucker optimality condition for constraint optimization problems. Now we notice that in the Karush-Kuhn-Tucker condition that we have derived in the last day, we have used only the first order partial derivative information for the constraint functions and of the objective function, and thus the Karush-Kuhn-Tucker condition that we have discussed on the last day is called the first order optimality condition for constraint optimization problems. Now in this lecture we are going to use the second order partial derivative information for the constraints and of the objective function, and using them we are going to find another optimality condition, and this optimality condition, as it is going to use the second order partial derivative information, is called second order optimality condition for constraint optimization problem. In this lecture we aim for discussing the second order KKT necessary and sufficient optimality conditions. So far we have been describing for constraint optimization problems the KKT necessary and sufficient optimality conditions. There you look at the conditions that I gave, you will find that those conditions were involving the first order partial derivatives of the objective function and of the constraint functions. Now similar to the unconstrained optimization problems, that in the unconstrained optimization problems at an optimum point the second order necessary and sufficient optimality conditions were found. Similarly, for constraint optimization problems, what are the necessary and sufficient optimality conditions in terms of the second order partial derivatives of the objective function and of the constraint functions? That is the agenda of this lecture. Neatly, we will consider two particular results. Those are second order KKT necessary optimality condition and second order KKT sufficient optimality condition to characterize or to identify an optimum point for a constraint optimization problem. We recall here that for an unconstrained optimization problem, we aim for identifying or characterizing a minimizer or a minimum point of a function of several variables. Let's suppose a function of n many variables. So here x is in Rn. An unconstrained optimization problem is this, that you aim for identifying a minimum point of this function, which if we assume to be continuously differentiable, then we all know for this unconstrained optimization problem, the first order necessary optimality condition is that if x bar is a minimizer of this problem, then at x bar we must have the gradient a null vector. Here, provided we are assuming that the function f is continuously differentiable. And the first order sufficient optimality condition for this unconstrained optimization problem is that if we are under the assumption that f is a C2 function that is twice continuously differentiable, then if we find a point x bar at which we have the stationarity condition happens to be true, that grad f x bar is vanishing, and if the objective function, this function f, is a convex function, then we all know that that implies the optimality, the minimality of this point x bar. So for an unconstrained optimization problem, for this problem, the first order necessary optimality condition is this, that the point x bar must be a stationary point, and the first order sufficient condition is this one, that if x bar is a stationary point plus the objective function f is a convex function, then these two conditions together will imply that the point x bar must be a minimum point of the function f. And for the same problem, for this unconstrained optimization problem, the second order necessary optimality condition is that assume the objective function f is twice continuously differentiable, because we are aiming for the second order necessary optimality condition. Here for first order necessary and sufficient optimality condition, we notice that we have assumed that the function f is just once continuously differentiable. F is belonging to C1 here. Here is also, sorry, here is also somehow I made a mistake here. For first order optimality condition, we must have f belonging to C1. For f belonging to C2 also, that is fine, that this condition will happen, but we need at least the function f is once continuously differentiable to identify the first order optimality conditions. In the second order optimality conditions, we need the function to be at least twice continuously differentiable. So provided f is twice continuously differentiable, a second order necessary optimality condition for this unconstrained optimization problem is that we are all aware of by now that if x bar is a minimum point of the function f, of the objective function f, then the point x bar must be a stationary point plus the Hessian of the objective function at the point x bar is positive semi-definite. That is the second order necessary optimality condition. We all know the stationarity, that is the first order optimality condition at the point x bar, plus you have the Hessian of the objective function at the point x bar positive semi-definite. So this is your second order necessary optimality condition. And the second order sufficient optimality condition for the unconstrained optimization problem, for this problem, is that if x bar is such a point that the point x bar is a stationary point, plus instead of this convexity in the first order sufficient condition, we consider the second order sufficient condition of convexity for the function f. So here, in addition to the stationarity of x bar, we also take out that the Hessian at the point x bar is positive definite. These two conditions together, in the second order sufficient condition, the point x bar is a minimum point of the function f. These all four conditions, the first order necessary condition, first order sufficient optimality condition, second order necessary condition, second order sufficient optimality condition, these all four optimality conditions we are all aware of for an unconstrained optimization problem. For a constrained optimization problem, we have gone through only the first order necessary and sufficient optimality conditions. Those are, if we quickly recall, we will find that for a constrained optimization problem, which is stated as minimization of a function of n many variables subject to certain constraint, that x belonging to some constraint set, say capital S, or the usual notation that we have taken up in the discussion of constraint optimization problem is that x belonging to capital F. Now, given this constraint optimization problem, the first order necessary optimality condition is that if x bar is a point, a feasible point, let's suppose this is your feasible set, and inside this feasible set, let's suppose the point x bar is located somewhere over here, and if x bar is a local minimum for this constraint optimization problem, then we can show that there does not exist any feasible descent direction for the function f at the point x bar. That is, if x bar is a minimum point of this constraint optimization problem, then we will see that for all feasible direction D, for all feasible direction at the point x bar, we must have the directional derivative of the function f at the point x bar greater than or equals to 0 if the point x bar is a minimum point of the constraint optimization problem. And these first order necessary optimality condition essentially have given us the KKT necessary optimality conditions, that in addition to the point x bar being a minimum point, if certain constraint qualification is satisfied, that is, if x bar is a local minimum and a constraint qualification is true, then these two conditions together implies that there exists Lagrange multipliers lambda bar and mu bar such that the point x bar together with these Lagrange multipliers will satisfy the KKT optimality conditions. So this triplet is a KKT point if the point x bar is a local minimum point. But here we also have to assume this crucial assumption that at the point x bar you must have a constraint qualification satisfied. Otherwise, the point x bar might not be a KKT point. We have seen such an example even for a convex optimization problem. If the constraint qualification is not satisfied, even if x bar is a local minimum point, the point x bar might not be a KKT point. We have seen such an example. Here, these lambda bar and mu bar are associated to the constraint functions, that if the constraint set capital F is given by in a structured manner by inequality and equalities, that this set capital F is set of all points x's belonging to some abstract set capital X, which is a non-empty open subset of the space Rn. This capital F is a set of all x's such that some inequalities are true for, let's suppose, m many inequalities, and some equalities hx's are equals to 0 for j is equal to 1 to say L. If the constraint set F is given by this structured manner by these inequalities and equalities, then these lambda bar and mu bar are having many components in lambda bar. Each of the components of lambda bar are associated with the constraint functions GIs, and this mu is belonging to RL, where each of the components of mu bar is associated to one of the equalities here, hx is equal to 0. We have seen that if x bar is a local minimum point of this constraint optimization problem and a constraint qualification is satisfied, then there must exist lambda bar with all of its components non-negative, and there exists mu bar such that this x bar, lambda bar, mu bar will satisfy all the four conditions in the KKT optimality conditions. So this is your first order necessary optimality condition. If x bar is a local minimum, then this condition will happen to be true, that x bar is a KKT point, but provided here the constant qualification has to be happened. And the first order sufficient optimality condition is that if x bar is such a feasible point of this constant optimization problem, that at x bar you have some Lagrange multipliers lambda bar and mu bar, so that this x bar, lambda bar, mu bar, this triplet satisfies the KKT optimality conditions. And if the problem, this constant optimization problem, is a convex optimization problem, by that we will mean that this function f is a convex function and this set capital F is a convex set, then we have seen that the point x bar must be an optimum point, a minimum point of the function f in the constraint set capital F. Here by now we know that in order to make this constraint set convex, we need to take these functions gixs convex, but these equality constraints are to be affine equality constraint. Otherwise, there is no guarantee that if we take these hxs are convex, there is no guarantee that this constraint set is going to be convex. Given this point x bar is a KKT point, plus this function f is convex, gi's are all convex, hj are affine, the point x bar must be a minimum point of the function f in the constraint set capital F. That we all have seen in the last lecture. Now in this lecture, we aim for discussing the second order necessary and second order sufficient optimality conditions for constraint optimization problems. For unconstrained optimization problems, we are all aware of the second order necessary optimality condition and second order sufficient optimality condition. But what would be second order necessary and sufficient optimality conditions for constrained optimization problem? For second order necessary and sufficient optimality conditions, we notice that the conditions are closely associated with some kind of convexity of the objective function. Here in the second order necessary condition, this essentially implies that the function f is crudely convex locally at the point x bar. Here also we have a similar condition that the Hessian is positive definite. So that is also related with convexity of the function f crudely locally at the point x bar. And similarly for constraint optimization problems, you know, this second order necessary and sufficient optimality condition also will go with some kind of convexity of an auxiliary function, not exactly of for the objective function f. And this auxiliary function for constraint optimization problem is the Lagrangian function. And basically we'll see that if some kind of positive definiteness of the Hessian of the Lagrangian is happen to be true at the point x bar, then that will give us some second order necessary and sufficient optimality condition for a constrained optimization problem. So to find this second order necessary and sufficient optimality conditions for constrained optimization problems, let us at first analyze the Lagrangian or the Lagrange function. Towards these, let me neatly write at first the constraint problem, which we usually denote by P. The constraint problem is minimization of a function of several variables subject to x is belonging to the feasible set F, which is given by x is belonging to some non-empty open subset of Rn. This set capital X is non-empty and these x's are satisfying m many inequalities gix less than equal to 0, I is for 1 to till m, together with some equality constraints ajx is equal to 0 for j is equal to 1 to till, let's suppose l many. Now for this constraint optimization problem, we define the Lagrangian or the Lagrange function given by L, a function of x, lambda and mu, where this x is belonging to the set capital X. Here this abstract set capital X, lambda is having many components, lambda is belonging to Rm and mu is belonging to RL. This M and L are the number of inequalities and equalities respectively. The expression of this L is given by Fx plus summation I is equal to 1 to L lambda I gix plus summation j is equal to 1 to L mu j hjx. So the function L is defined on this set. Or also, in order to be more erudite, better here we take all the components of lambdas are non-negative. Keeping in mind that these lambda and mu are going to be the KKT multipliers. Now, given this definition of Lagrange function, we have seen that if these functions, the objective function, constant functions are of C1 functions inside the constraint set capital F for all I and for all j's, and the point x bar is a KKT point associated with the Lagrange multipliers as lambda bar and mu bar, then we have seen that the point x bar, lambda bar, mu bar must be a stationary point of this Lagrange function. We have seen this. Here you may please relook the lecture note on KKT optimality condition, the lecture note of the previous lecture. You please relook and there you will find that given these objective and constant functions are continuously differentiable in the constraint set and this point x bar is a KKT point, then we can show that the point x bar together with this lambda bar and mu bar, this is a stationary point of this Lagrange function Lx lambda mu, the function that I have defined over here. So if the functions, these objective function, constant functions are C1 functions, then we notice that if certain constraint qualification is satisfied at the point x bar, and if the x bar is a minimum point, then obviously this x bar lambda bar mu bar is going to be a stationary point of the function L. So we can just think of an unconstrained optimization problem, that minimization of this function Lx lambda mu to identify a minimum point or possible candidates to be minimum of the constraint optimization problem capital P. Because any possible candidate to be minimum for this constraint optimization problem is going to be a stationary point of this function, this Lagrangian function. So to find a minimizer, a minimum point of this constant optimization problem, we can just crudely go for analyzing the unconstrained optimization problem, minimization of this Lagrangian function. So here we notice that with the help of this Lagrange function, these first order necessary optimality condition for the constraint optimization problem can be equivalently written as x bar lambda bar mu bar is a stationary point of the Lagrangian or the Lagrange function Lx lambda mu. Here every time I am separating out this x with lambda mu with a colon to mean that they are of different categories. That x bar is essentially the variable vector for the original given problem, the constraint optimization problem, and lambda and mu, those are some auxiliary variables, the Lagrange multiplier vectors in the necessary optimality conditions. So here to find a first order necessary optimality condition, we notice that we can just go for identifying a necessary optimality condition for the unconstrained optimization problem, the minimization of the Lagrangian function. If this is possible for first order necessary optimality condition, let us try to see if this is also possible for the second order optimality condition, that if first order optimality condition for constraint optimization problem can be identified with the help of an unconstrained optimization problem, can it be possible also to identify second order necessary and sufficient optimality conditions with the help of this unconstrained optimization problem, minimization of this Lagrange function? Towards this, let us look a bit more on this Lagrange function. Define a restricted Lagrangian or the restricted Lagrange function as follows, that given a KKT point, say x bar together with the Lagrange multipliers as lambda bar mu bar, we consider the function L of x but with given values of lambda and mu by lambda bar and mu bar respectively. So we consider this function Lx lambda bar mu bar. These lambda bar mu bar are given values and we call it as restricted Lagrangian or restricted Lagrange function denoted by L bar x, and this function we consider in the set capital X. Defining this restricted Lagrangian, we immediately notice the following very interesting fact, that we see that the first point inside the constraint set, that means inside X belonging to the feasible set capital F, we have L bar X. This value is less than or equals to Fx, because you notice that for X belonging to capital F, we have these Hjx values are all zeros, so this entire summation part is equal to 0, and for X belonging to capital F, we see that these Gix's are less than equal to zeros, and therefore this summation is less than equal to 0 when X is belonging to F, because the components of lambda bar are all non-negative. So certainly we have this inequality. Not only that, we also see that we have the value of the restricted Lagrangian at the point x bar is identical to the value of the objective function at x bar, because this triplet satisfies the KKT optimality conditions, and inside of the KKT optimality conditions we have the complementary slackness condition lambda I times gi is equal to 0, and therefore at the point x bar we have this summation, this part is equal to 0, and hence we have this equality that the values of L bar and F at the point x bar are identical. And then from this second condition, this condition, we see that we have a very interesting implication, which is that if x bar is a local minimum of this restricted Lagrangian inside the set capital F, then certainly the point x bar is a local minimum of the original objective function f in the set capital F. This is due to very simple observation that we notice that if x bar is a local minimum of this restricted Lagrangian, then certainly there exists a neighborhood, a local neighborhood of the point x bar, such that in that local neighborhood L bar x bar is the minimum most value of L bar, right? That is, we have this inequality that L bar x bar is less than equal to L bar x for all x inside the intersection of a ball of radius delta with the feasible set, and from here we have that this L bar x is always less than or equal to fx inside this feasible set, and therefore we have L bar x bar is less than equal to fx for all x belonging to this set intersection of this ball for some delta value delta greater than 0 with the feasible set capital F, and we notice that this left hand part L bar x bar is equal to f x bar due to this second observation, and hence we have f x bar is less than equal to f x. This inequality is true inside this local neighborhood of the point x bar, and hence the point x bar is a local minimum of f inside the feasible set capital F. And therefore, fascinatingly, if a KKT point is given to us, then we go for identifying the second order optimality condition checking only for on this function to ensure that the point x bar is certainly a local minimum point. So given a KKT point, you construct the restricted Lagrangian and check if the second order sufficient optimality condition for unconstrained optimization problems is satisfied for these restricted Lagrangian function, and once satisfied, then you can certainly ensure that the point x bar, this given KKT point, is a minimum point of the constrained optimization problem. So a second order sufficient optimality condition for a constant optimization problem is given by the second order sufficient optimality condition for an unconstant optimization problem with the objective function as the restricted Lagrangian function. So next we neatly write here the second order necessary and sufficient optimality condition for a constant optimization problem with the help of the restricted Lagrangian function. As a result, a straightforward result by the observation 1, 2 and 3 that just I have described for restricted Lagrangian function, we have the second order necessary and sufficient optimality condition for a constant optimization problem as follows. That consider the constant optimization problem P with the objective and the constraint functions. They are of C2 functions inside the constraint set for all I and j, and suppose x bar be a KKT point of the problem P with the Lagrange multipliers, say lambda I bar greater than equals to 0 for all the components of lambda bar I is equal to 1 to m, and mu g bar, which are components of mu bar. Then the second order necessary and sufficient optimality conditions for the constraint problem is as follows. If the Hessian of the restricted Lagrangian function is positive semi-definite for all x belonging to the constraint set, then we must have that the point x bar being a stationary point of the restricted Lagrangian function, a global minimum point of the constraint problem. If, however, this Hessian of the restricted Lagrangian is positive semi-definite in a local neighborhood of the point x bar, that is inside a ball of radius delta centering at x bar intersection with the feasible set. If this is true, then x bar is a local minimum point of the function L bar and hence a local minimum point of the constraint problem. And the third point is that if you find the Hessian of the restricted Lagrangian only at the point x bar is positive definite, then the point x bar must be a strict local minimum of the restricted Lagrangian function and hence of the objective function of the constraint problem. So this will imply now then x bar is a strict local min of the problem. All these three conditions, we note that they are sufficient second order optimality conditions. And for a necessary optimality condition, we have that once the point x bar is a negative point, we must have the Hessian of the restricted Lagrangian at the point x bar is positive semi-definite provided the point x bar is a local minimum point of the constraint problem. So here goes a second order necessary optimality condition for a constraint optimization problem, and here goes second order sufficient optimality condition for a constraint optimization problem. Now here we notice that these second order sufficient conditions, they require checking positive definiteness or positive semi-definiteness of these Hessian matrices, these or these, inside this entire region or inside the entire feasible region. But checking definiteness of this Hessian inside this entire feasible set or inside even these in a local neighborhood is a bit tedious and practically very difficult. So people have identified some refined version of this second order necessary condition and second order sufficient condition for optimality by checking the definiteness of these Hessian matrices in a restricted set of directions, and that restricted set of or cone of spatial directions is defined as follows: that for a given KKT point x bar, you consider to identify the Lagrange multipliers lambda I bar and mu j bar, and accordingly go for constructing this restricted Lagrangian function L bar. And in the definition of L bar, we require L x lambda bar mu bar, and where L is given by this expression, and you know in this expression even we can go for a reduced version of this definition, that once the restricted Lagrangian is to be constructed, then we see that the lambda I bar values for which the I indices are not active, then lambda I bar values for those non-active indices are equals to 0. So we can even replace this summation not for all I is equal to 1 to m, but you can restrict it to be lying inside only the active set of indices at the point x bar. And with that reduced version of this summation, by just considering this summation over this I x bar, you can even go for finding this L bar x. Eventually they will give the same expression whether or not you are taking the summation over the active indices or in the entire I is equal to 1 to m. And then after identifying the expression for the restricted Lagrangian L bar for a given KKT point, we construct the following cone of spatial directions, and we will find that inside the would be constructed this cone of spatial directions. If these Hessian matrices, these and these, are definite only on these cone of spatial directions, then also these two implications are true. And that will greatly reduce our task to identify the definiteness. Instead of this entire region here or here, you just go for identifying definiteness on these cone of directions, and then these two sufficient conditions will be holding to be true. Towards this reduction of effort, we now construct the cone of spatial directions as follows. That at the point x bar, you go for identifying what are active set of indices, and inside the active set of indices, go for bifurcating the active set of indices into two sets as follows. That let's suppose the active set of indices at the point x bar is given by set of all those i's for which gi x bar is equal to 0, the usual definition of active set of indices, and accordingly these gi's are called as binding constraints. Now we break these ix bar active set of indices into two sets. Those are I plus and I naught, where I plus is the set of all those indices, those are active at the point x bar, and we have the corresponding Lagrange multipliers greater than 0, and I0 is set of all those active set of indices for which lambda I bar is equal to 0. We notice that inside of this lambda bar, which has m many components, non-negative each of them, but corresponding to the inactive set of indices, that means those i's which are not in this index set, those components will be equals to 0, right, due to the complementary slackness condition. But for those small i's which are belonging to this active set of indices, we are not sure whether lambda I bar is greater than 0 or is equal to 0. They can be anything greater than 0 or equals to 0, right? So we break this active set of indices into two parts, I plus and I naught. We notice that this I plus union I naught is the entire active set of indices ix bar. Commonly, this set I plus is referred as strongly active index set, and this set I naught is called weakly active index set. Now, after constructing this I plus and I naught, the set of these spatial directions at the point x bar, we denote by Cx bar as the set of all non-null directions in the n-dimensional Euclidean space, the space Rn in which the variable vector x is lying. The set of all those non-null d's such that gradient of Gix bar transpose D is equal to 0 for the strongly active index set, and for weakly active index set this inequality has to be less than equal to 0, and in addition we must also have for the equality constraints this term is equal to 0 for all j is equal to 1 to till L. You consider these set of directions D's which are satisfying all these three conditions, and accordingly we consider this set. Notice that this Cx bar is a cone provided you are taking out the null vector also inside this set. And after constructing these set of spatial directions, those non-null directions which are satisfying all these three conditions, I now go for writing out the KKT necessary and sufficient optimality condition in the second order. The KKT second order necessary optimality condition is as follows, that we consider the problem P with all the functions, objective and constraint functions, are twice continuously differentiables, maybe inside the entire feasible set for all I and j. Now, if the point x bar is a local minimum of the problem P and some constant qualification, like the condition we have taken, the linearizing cone at the point x bar as dual is equal to the tangent cone at the point x bar, its dual, if they are identical, then we have seen that if x bar is a local minimum point, then the point x bar must be a KKT point of the constant optimization problem P. This condition here is usually referred as the regularity condition. If this regularity condition or some other conditions are not satisfied, in addition to this local minimality of the point x bar, the point x bar might not be a KKT point. We have seen such an example, that towards the end of the last day's lecture, we were giving a convex optimization problem in which the point x bar is a local minimum point, but that point is not a KKT point. The very reason is that you will find that in that example, this condition is not satisfied. So we consider that x bar is a local minimum point together with this condition or some other similar conditions are satisfied, which we refer as the constraint qualification condition. Maybe you can also consider that the vectors gradient of gi's at x bar for I belonging to the active set of indices together with the vectors gradient of hj x bar for all j. You consider all of these directions, all of these vectors, and if this set is linearly independent, then also we can show that if x bar is a local minimum point plus the linear independence of this set also will imply that the point x bar is a KKT point of the constraint problem. So some kind of constant qualification, some kind of this condition or some other conditions will detail in the next lecture. Some other conditions which are usually referred as constraint qualifications. Some condition on the constraint set. So that if one of those conditions is satisfied and x bar is a local minimum point, then the point x bar is certainly going to be a KKT point. So we assume here is that x bar is a local minimum point and some constant qualification. Maybe let's suppose we consider this condition which we call as linear independence constant qualification, popularly abbreviated as LICQ. And LICQ holds, then the point must be a KKT point for which we'll certainly have some Lagrange multipliers, say lambda I bar greater than equals to 0 for all I and mu j belonging to R, mu j bar for all j. With this lambda bar and mu bar, the restricted Lagrangian, the function L bar x, which is the Lagrangian function where the values of lambda and mu are lambda bar and mu bar respectively. This L bar has positive semi-definite Hessian at the point x bar for all directions d in Cx bar. That is, we have d transpose, the Hessian of the restricted Lagrangian at the point x bar times d is greater than equals to 0 for all d belonging to the special direction set Cx bar. So this is your second order necessary optimality condition for constrained optimization problem. That if x bar is a local minimum point and some constant qualification is holding to be true, then the restricted Lagrangian must be positive semi-definite in the set of all directions in Cx bar. For a proof of this result, you may please visit the book by Bazara, Serali and Sethi on the third edition of the book on the page number 216, where you will find the theorem 4.4.3 where this result is proved. For a second order sufficient KKT optimality condition, we will see that if the Hessian of the restricted Lagrangian is positive definite inside this Cx bar at the point x bar, then the point x bar is a strict local minimum point of the constrained optimization problem. We neatly write out this sufficient condition as follows, that KKT second order sufficient optimality condition, which states that consider the constraint optimization problem P with the objective and constraint functions all are having continuous second order partial derivatives inside the feasible set, and let the point x bar is a KKT point with Lagrange multipliers lambda I bar greater than equals to 0 for all I and mu j bar unrestricted in sign for all j. Then if the Hessian of the restricted Lagrangian at the point x bar satisfies the property that it is positive definite for all directions inside the set of direction Cx bar, then x bar is a strict local minimum of the constraint optimization problem. For a proof, you may please visit the page number 214 of the same Bazara book in its third edition, where you will find the theorem number 4.4.2 where this result is proved. I would rather consider a numerical example where this KKT second order sufficient optimality condition will be checked. For example, consider the constraint optimization problem, which is stated as minimization of a function of two variables x1 x2, which is given by x1 minus 1 square plus x2 subject to x1 plus x2 minus 2 is less than equal to 0 and x1 minus x2 minus 1 is equal to 0. Consider this problem, and here it is given that the point x bar having components x1 as half, x2 as 3 by 2. This point x bar is a KKT point with the Lagrange multipliers lambda bar is equal to 0 and mu bar is equal to minus 1. Here let me write lambda 1 bar and mu 1 bar because I have also indexed up here g1 and h1. Given this x bar a KKT point, now check if the second order sufficient optimality condition is satisfied, and hence you can declare that the point x bar is a local minimum point of this considered optimization problem. To check if the second order sufficient optimality condition is satisfied or not at the point x bar, we need to construct the set Cx bar. To find the set Cx bar, we find the active set of indices Ix bar. We notice that At the point x bar, we have g1 x bar is equal to 0, and therefore I x bar consists the index number 1. And for these active set of indices, we have the strongly active set of indices is equal to the null set, because we have the associated lambda 1 bar is equal to 0, and therefore I plus is equal to null, but the weakly active set of indices is equal to the index 1. So the restricted Lagrangian function is L bar. X has two components, x1 x2, and lambda 1 bar mu 1 bar, which is given by fx plus lambda 1 bar gx. Lambda 1 bar is equal to 0, and therefore we will end up with mu 1 bar h1. So you will have here minus h1x. This is your restricted Lagrangian function. Now we consider the set Cx bar. Cx bar is a set of all those non-null directions in the two-dimensional Euclidean space, such that if we are writing this d1 d2 by a vector d, we have gradient of g1 at x bar transpose d is going to be, as g1 is belonging to this weakly active set I naught, so we will have here this less than equal to 0, and together with grad h1 x bar transpose d is equal to 0, which gives the set Cx bar is equal to the set of all those non-null vectors in R2, such that here you compute the gradient of g1 x bar. You will find the gradient as 1 1. So you will have here d1 plus d2 is less than equal to 0, and this portion will give us d1 is equal to d2, and hence Cx bar consists of those d1 d2 such that d1 is equal to d2, and hence here if you plug, then you will find that d1 is less than equal to 0 and d1 is equal to d2, right? Now we go for checking whether inside this set Cx bar the Hessian of L bar is positive definite. We compute the Hessian of the restricted Lagrangian at a general point, which gives us the Hessian of f minus the Hessian of h1x. For the h1, we see that we have a linear function, and hence the Hessian will be a zero matrix, and for f we will have 2 0 0, and therefore the expression that d transpose the Hessian of the restricted Lagrangian at the point x bar times d is equal to, we have 2d1 square for all d1 d2 inside the set Cx bar, because we have d1 is equal to d2, and this 2d1 square is certainly greater than 0, because we have here d less than equal to 0 and d1 is equal to d2 will give us, when this d1 d2 is not null, we'll certainly just have d1 is less than 0. So here we will have 2d1 square greater than 0 for all d1 d2 belonging to this set Cx bar, and therefore the point x bar by the second order sufficient KKT optimality condition is a local minimum of the constraint problem. You can even check that this point x bar is a local minimum geometrically. Quickly you can just go for drawing out the feasible set, and in the feasible set you will find that so the contours of these objective function, which are parabolic functions, will give us a minimum value at the point x bar. I am just keeping a home task here, that geometrically you figure out that this point x bar is certainly a local minimum point of this objective function f on this constraint set. Now I stop the lecture here, and these completes the necessary and sufficient optimality condition in terms of first order, second order, and all for constraint optimization problems. In the next day, I will quickly visit a very short visit on several other constraint qualification conditions and their interrelationships, satisfying which a local minimum point of a constraint optimization problem can be ensured to be a KKT point. So in the next lecture, our agenda will be a short discussion on constraint qualification. Thank you all for all of your kind attention.